I welcome you all for the fifth lecture on Fourier series and transforms. Today we will discuss Fourier transforms, properties of Fourier transforms. As we discussed in lecture 4 about Fourier cosine transform and Fourier sine transforms, we obtained these two transforms from the Fourier cosine integral and Fourier sine integral. We will do something like that to find the Fourier transform. And to obtain Fourier transform, we write down the Fourier integral in complex form, and then finally we define Fourier transform. For a given non-periodic function f of x, we can define the Fourier integral by equation 1. F of x is equal to integration from 0 to infinity aw cos of wx plus bw sin of wx dw, where aw and bw are defined below. Now in equation number 1, just substitute the values of aw and bw. We have the next expression. Now just rewrite this expression as a double integral. F of v will be common and we have cos wv cos wx plus sin wv sin wx. First we are integrating with respect to v. Limits of integration are from minus infinity to plus infinity. Then integration with respect to w from 0 to infinity. Now in this Fourier integral, we can combine the terms with cos wx cos wv, and we can write down this one as cos of a minus b. So finally we have equation number 2. So f of x is now 1 upon pi 0 to infinity. Inner integral is minus infinity to plus infinity f of v cos of wx minus wv dv. See this expression in the red bracket. There are three variables w, x and v. We are integrating with respect to v, and then after integration we are integrating with respect to w. So we are treating x as constant. But in the inner integral we are integrating with respect to v. So w will be treated as a constant and this whole integral will be a function of w. So we are claiming that this function, this inner integral after integration, this is an even function of w, and we can easily prove this thing. Let gw be the function inner integral minus infinity to plus infinity f of v cos of wx minus wv dv. I'm not writing here x because throughout this integration we are treating x as constant. Only v and w are variables. So after integration we substitute the value of v as minus infinity and plus infinity, and we have just function of w. Now replace w by minus w. We get g of minus w on the left side. Replace w by minus w in the integral, that is the cos term. Simplify this and we know that cos of minus theta is cos theta, and we get again g of w. So this inner integral is an even function, and we know that for an even function minus a to a f of x dx is 2 times 0 to a. So I'm just using this property, and equation number 2, f of x can be written as 1 upon pi 0 to infinity g of w dw. So we are just rewriting this integral and changing the limits of integration from minus infinity to plus infinity, and we have finally this expression. I have to divide this by 2, so it is 1 upon 2 pi minus infinity to plus infinity g of w dw. So finally equation 2 can be rewritten as equation number 3. F of x is 1 upon 2 pi, and the limits of integration for both the integrals are now minus infinity to plus infinity. As discussed for the function GW, now we define HW. This is integration from minus infinity to plus infinity f of v sine of wx minus wv dv. From 4, we can say that this function hw is an odd function of w. We can easily verify this. Replace w by minus w in equation number 4. Then only sine term will change, and we know that sine of minus theta is minus sine theta. So we see that h of minus w is minus hw. Now using the property of odd functions, that integration of an odd function from minus a to a is always 0. So we can say that 1 upon 2 pi minus infinity to plus infinity h of w dw is 0. So finally we have equation number 5, that 1 upon 2 pi minus infinity to plus infinity. I'm just substituting the value of hw from equation number 4, and I have equation number 5. Now I'm rewriting equation number 3, that is the Fourier integral of function f of x. So f of x is equal to 1 upon 2 pi double integral from minus infinity to plus infinity f of v cos of wx minus wv dv dw. That is third equation, right? Now we multiply equation number 5 by iota on both sides and then add to equation number 3. So on adding, left hand side will be just f of x, because left hand side of equation number 5 is 0, so iota times 0 is 0. And on the right hand side, we can simplify this expression. We have double integral minus infinity to plus infinity f of v. Now we have cos wx minus wv plus iota times sine of wx minus wv. Now we use the result that e raised to power iota theta is cos theta plus iota sine theta. So we can combine this expression, and finally we have f of x is equal to 1 upon 2 pi minus infinity to plus infinity f of v e raised to power iota times wx minus wv dv dw. Rewrite this exponential function. Just separate the terms with x and v. Now we just rewrite this expression, and now f of x can be written as 1 upon square root of 2 pi minus infinity to plus infinity, and the inner integral is 1 upon root 2 pi minus infinity to plus infinity f of v e raised to power minus iota wv dv, and I'm writing it e raised to power minus iota wx, because in this inner integral we are integrating with respect to v, so w is constant for this part, so I can take this outside the integral e raised to power iota wx. I have marked this inner integral as star. The expression in the bracket, which I marked as star, is a function of w, and this is denoted by f cap w or by capital F of w, and it is called the Fourier transform of the function f of x. So we just replace v by x. We can do that because finally we just put the limits minus infinity to plus infinity. So for a given function f of x, the Fourier transform is defined as equation number 6, 1 upon root 2 pi integration from minus infinity to plus infinity f of x e raised to power minus iota wx dx, and the Fourier integral can be written as 7, that f of x is 1 upon root 2 pi minus infinity to plus infinity f cap w. This is the Fourier transform e raised to power iota wx dw. So this f cap is the Fourier transform of function f of x, and function f of x is called the inverse Fourier transform of f cap w. Just take care of the sign of exponential function. In Fourier transform, we have f of x e raised to power minus iota wx. And in the Fourier integral, it is e raised to power iota wx. See equation number 7. Next is the result related to the existence of Fourier transform. It says that if a function f of x is absolutely integrable on the x-axis and piecewise continuous on every finite interval, then the Fourier transform of function exists, and it is given by this equation f cap w, which is equal to 1 upon root 2 pi minus infinity to infinity f of x e raised to power minus iota wx dx. Now, numerical problem. For a given function f of x, we have to find out its Fourier transform. So our function f of x is e raised to power minus ax if x is greater than 0, and it is 0 if x is less than 0. So to find out its Fourier transform, we just substitute the value of the function in the formula f cap w and simplify the integration. So Fourier transform of e raised to power minus ax is 1 upon root 2 pi integration from minus infinity to plus infinity. When you substitute the value of the function, your function is 0 from minus infinity to 0. So the integral is now 0 to infinity e raised to power minus ax e raised to power minus iota wx. Collect the exponential function. Now it is e raised to power minus a plus iota w into x dx. We can integrate it, it's easy, and finally we have this answer. And when we are putting the lower limit x equal to 0, we get the result. When we are putting the upper limit, that x tends to infinity, this whole part is 0. You can see the expression I have written, that I can break this exponential function e raised to power minus ax and e raised to power minus iota wx. And we know that e raised to power iota theta is cos theta plus sin theta. So when x tends to 0, cos and sin, they may oscillate minus 1 to 1, but it's going to be something finite. And the exponential function e raised to power minus ax, it will tend to 0 because it is given that a is greater than 0. So the upper limit is going to be 0. When we say x tends to infinity, the exponential function will tend to 0. Consider one more problem. Find the Fourier transform of the function f of x, which is 1 if mod x is less than 1, and it is 0 if mod x is greater than 1. Write down the formula of Fourier transform. Now put the value of the function. So now integration will be from minus 1 to 1 as the function is 0. Otherwise, integrate this. Put the lower limit minus 1 and upper limit as 1. Simplify this function. We have the final answer as square root 2 upon pi sine w divided by w. Try these numerical problems and find the Fourier transform of these three functions. Now, properties of Fourier transform. First property is about the linearity of Fourier transform. It says that Fourier transform is a linear operator. It means that if f and g are two functions and their Fourier transforms exist, then the Fourier transform of a times f of x plus b times g of x is equal to a times Fourier transform of function f plus b times Fourier transform of g, where a and b are constants. Its proof is very easy. We just apply the definition and simplify the expression. So Fourier transform of AF plus B times G is equal to 1 upon root 2 pi minus infinity to plus infinity A times F plus B times G. Multiply this by e raised to power minus iota wx dx. Now it's very easy. We can separate this function af plus b times gx. Now we have two integrals. I have marked them as star 1 and star 2. The first expression is the Fourier transform of function f of x, and star 2 expression, it is the Fourier transform of function g, and hence we have the result. Second property is about the Fourier transform of the derivatives. Let f of x be continuous on the x-axis and function tends to 0 as mod x tends to infinity. Further, let f dash x, first order derivative of function f of x, be absolutely integrable on the x-axis. Then Fourier transform of f dash x is equal to iota times w Fourier transform of function f. Now for this proof, we again start by the definition. Fourier transform of f dash x is 1 upon root 2 pi integration from minus infinity to plus infinity f dash x and e raised to power minus iota wx dx. Now we just integrate this, integrate by part. We will take exponential function as the first function and f dash x as the second function. Integrate this. After integration we have e raised to power iota wx, integration of f dash x, that is the second function, and it is f of x. Now put the limits minus infinity to plus infinity, then again minus sign, integration from minus infinity to plus infinity, derivative of first function, that is e raised to power minus iota wx into minus iota w, and the integration of second function, that is f of x dx. Now the first part of this integration, where we have to put the limits minus infinity and plus infinity, this is 0 because function f of x tends to 0 as mod x tends to infinity, and the exponential function, that is e raised to power minus wx dx, it is going to be something finite, maybe oscillating, so 0 cross finite thing is going to be 0. So we just have the second integral part, and we can rewrite this as iota times w, and see the integration. This one is the Fourier transform of function f of x, and hence we have the result. One more numerical problem. Using the property of Fourier transform of derivatives, we will find out what is the Fourier transform of second order derivative of a function f of x. Again, we can solve this problem directly also by definition. We just integrate that twice, or we can use the last property also. Now using that property, Fourier transform of f dash x, this is equal to iota times w Fourier transform of f of x. In this property, replace f of x by f dash x, that is first order derivative. So we can say that Fourier transform of f double dash x is Fourier transform of f dash x and then its derivative. So I'm just rewriting second order derivative in this form. Now using the property of Fourier transform for derivative, this is going to be iota times w Fourier transform of f dash x. Now we again use the property that what is the Fourier transform of f dash x? This is iota w Fourier transform of f of x. We can simplify this and finally we have minus w square Fourier transform of f of x. One more numerical problem, it's very important and little tricky. Find the Fourier transform of e raised to power minus x square. We just apply the formula of Fourier transform. So its Fourier transform is 1 upon root 2 pi integration from minus infinity to plus infinity e raised to power minus x square, that is a function, multiplied by e raised to power minus iota wx dx. Combine this exponential function, we have now e raised to power minus x square plus iota wx. Now we have to simplify this integration. To simplify this, first we rewrite this one as whole square exponential and the power we write as this one. I am adding iota square w square by 4 and subtracting the same thing. I can take e raised to power iota square w square divided by 4 common, and now we have equation number 1, that is integration is from minus infinity to plus infinity e raised to power minus x plus iota w by 2 raised to power 2. Now we use substitution method to evaluate this integral in equation number 1. For this we are defining v, a new variable, as x plus iota w by 2. Then we can rewrite this integral as equation 2, e raised to power minus w square by 4 divided by root 2 by integration from minus infinity to plus infinity e raised to power minus v square dw. Now the question is how to evaluate this expression in 2. Now how to integrate this expression e raised to power minus v square dv minus infinity to plus infinity. So we are squaring this expression and then we say take its square root. Now we simplify the inner part, that is square of this expression, required integral. Now we can write down this one as product of two integrals, and limits of integration are from minus infinity to plus infinity. Variable is v. Now we keep variable v or we define some new variable. It hardly make any difference because finally we have to just substitute the limits as plus infinity and minus infinity. So I am changing the first integral and writing the variable as x, and in the second part I am writing this one as variable y. Now using the property of double integral, I can combine the product of these two single integrals as a double integral, and we have expression in second line that double integral from minus infinity to plus infinity e raised to power minus x square plus y square dy dx. For this one I am using the property that if you have a double integral where limits of integration are constant, that is independent of the variables, and the function f of xy can be written as a product of function of only x and function of only y, then we can simplify this integral as single integrals. One is going to be function of only x and other one is going to be function of only y. So finally we have this single integral as a double integral in Cartesian coordinates. Now we change everything into polar form. X equal to r cos theta, y equal to r sin theta, and using the Jacobian, dy dx will be replaced by r dr d theta e raised to power minus r square, and we are integrating in whole of the xy plane, so r will change from 0 to infinity and theta will change from 0 to 2 pi. Now we can again integrate this. Just put r square equal to t, and after simplification we have root pi. So finally we substitute this value and we have Fourier transform of e raised to power minus x square is given by 1 upon root 2 e raised to power minus w square divided by 4. Consider this example where Fourier transform of a function e raised to power minus x square is given to you, and using this you have to find out the Fourier transform of x into e raised to power minus x square. So given function is e raised to power minus x square, we can find out its first order derivative f dash x, and it is minus 2 times x e raised to power minus x square. Now we use the property of the Fourier transform of derivative of a function, which is f Fourier transform of f dash x is iota w Fourier transform of function f. Now put the value of the function f and its derivative f dash x in this formula. On the left hand side, minus 2 I can take common. We have Fourier transform of x e raised to power minus x square. On the right hand side, we can put the value of Fourier transform of the function e raised to power minus x square. Divide by minus 2, we have the result. Convolution theorem for Fourier transforms. See equation number 1 here. For given two functions f and g, the convolution is defined as integration from minus infinity to plus infinity f of p g of x minus p d of p. Here we are integrating with respect to p, substituting the limits from minus infinity to plus infinity, and finally after integration we have a function of x. That function is called convolution of f and g. Here we can interchange the role of f and g. We can have g of p and f of x minus p. Even then we have the same result. So this theorem for Fourier transform, convolution theorem, it says that f and g are piecewise continuous, bounded and absolutely integrable on the x-axis, then the Fourier transform of f star g, that is convolution of f and g, is equal to root 2 pi Fourier transform of f and Fourier transform of g. To prove this result, we use the definition of Fourier transform, and there are three main steps. First step, write down the definition of Fourier transform. Substitute the value of convolution. Write down this one as a double integral. Second step, change the order of integration. Simplify. Third step is substitution, and then finally we have the result. So come to the proof of this. Fourier transform of f star g is 1 upon root 2 pi integration from minus infinity to plus infinity f star g e raised to power minus iota wx dx. Now use equation number 1 and put the value of f star g. We have the second expression. Write down this one as a double integral. And finally we have double integral minus infinity to plus infinity f of p g of x minus p e raised to power minus wx dp and then dx. Now step 2, change the order of integration. Here limits of integration are constants, minus infinity to plus infinity, so we can just interchange the order by replacing dx and dp. So we have now second expression. Now we go to step number 3, substitution method. For the function g, we have g of x minus p. We define x as p plus q. That is, I am defining x minus p equal to a new variable, that is q. So dx is given by dq. In the inner integral, we are integrating with respect to x. So p will be treated as constant. So dx is equal to dq, and limit of integration will be from minus infinity to plus infinity. There will be no change except dx is now replaced by dp. In the exponential function, replace x by p plus q. We have again double integral. Now rewrite this exponential function and separate the term with p and q. We have e raised to power minus iota wp. I have marked by star, and second expression is e raised to power minus iota wq dq, and then integration with respect to p. Now in the inner integral, we are integrating with respect to q. P is constant, so f of p and the exponential function e raised to power minus iota wp, we can take it outside this integral and we can rewrite as the next line. Now in the inner integral is now minus infinity to plus infinity g of q e raised to power minus iota wq dq. Multiply by root 2 pi, divide by root 2 pi. Now the expression which I have underlined in red, this is the Fourier transform of g of x. This is going to be a function of only w, hence it is constant. You can write down it outside this integral, and we have root 2 pi f of gx, that is Fourier transform of g. Now see the inner integral now, 1 upon root 2 pi minus infinity to plus infinity f of p and the exponential function, and by definition this is the Fourier transform of f of x, and hence we have the final result for convolution f star g.